In this video, we will talk about reverse osmosis. At the top of the box, we indicate the number of each type of particles on each side. In this animation, the front wall and the back walls are invisible. What may look like erratic particle motion is really particles bouncing off the invisible front and back walls. The small red particles are able to pass through the walls and this membrane, whereas the white large particles are not. In equilibrium condition, there will be therefore some red particles on both sides of the membrane, whereas the white large particles will always only be on the right side. This means in an equilibrium condition, there will be a greater number of total particles on the right side of the membrane than on the left side. We call this process osmosis. Suppose we want to reverse this process and move all the red particles back to the left side, at least many red particles as we can. We can do this through the process called reverse osmosis. If the piston on the right moves towards the left, we can try to force the red particles through the membrane back to the left side. Notice the number of red particles at the top screen. On the right side of the membrane, the number of red particles becomes 0. Next, we will show you reverse osmosis in a different way. Chemical plant uses reverse osmosis to further treat water after the ultrafiltration process. Reverse osmosis membranes are constructed from a membrane flat sheet which comprises of 3 layers: a polyester fabric support base, a microforce poured sulfone layer, and a 0.2 micro-thick polyamide barrier layer. The polysulfone layer strengthens the very thin barrier layer. It is the barrier layer that removes nutrients, chemicals, bacteria, and viruses from the water. The membrane flat sheet is combined with a feed channel spacer. This provides turbulence and creates space between the membrane sheet for further treat of water. A sheet of permeate spacer is added to the membrane sheet and the feed channel spacer. This enables the final recycled water product or permeate to flow evenly across the entire membrane surface, even under high pressures. The back of the membrane is completely sealed to the edge of the permeate spacer. These membrane sheets are glued along each other, 3 exposed sides, and rolled along the core tube. Feed water is forced through the feed channel spacer and into the barrier layer of the membrane. Water passes through the membrane surface into the permeate channel. It flows into a spiral direction and collects in a core tube. The water in the final recycled water product or permeate. There are 7 spiral wound elements loaded in a pressure vessel. One of the end adapted is connected to the last element and the pressure vessel is sealed. Feed water can be introduced. Feed water is pumped at high pressure into the vessel. As it travels, small molecules like water passes through the membrane, whilst large particles such as salt, bacteria, viruses do not. The final recycled water product is collected from the end of the element vessel. The concentrated or rejected from the vessel flows into another stage, producing more recycled water. At some merits are the 6 reverse osmosis treatments. In our next video, we will show you how reverse osmosis works in our water processing industries. The osmotic pressure can be calculated using this formula. Thus, pi is equal to the m r t, where m is the molarity, r is the molar gas content, and t is the absolute temperature. Now, calculating for m, it is the number of moles per liters. We have 13 grams of sucrose. Now we need the number of grams per mole. So we have 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. Now multiply the 12 by the atomic weight of what? Carbon. Do same for hydrogen, and we do same for oxygen. On the total distance, after computing the total, we have the distance to be 342.22 grams per mole of sucrose. And now we have 125 ml. Doing unit conversion, 10 to the power 3 ml is equal to 1 liter. Computing this, you are going to get 0.304 mole per liter. Now putting it into the main formula, we have m to be equal to 0.304 mole per liters, and the r, which is the molar gas constant, to be equal to 0.08314 liter bar per mole per Kelvin. Multiplying the temperature in the absolute temperature, which is 273 plus 20. Now computing this, you get pi to be equal to 7.4 bar. Thank you.